Hello, and welcome to the Code Signing and Windows presentation for the PDC 2008. My name is Ben Nick. I'm a program manager on the Windows Security Cryptography team. I've been on the security team now for about 4 years and worked with code signing and code signing technologies for about 3 years now. In today's presentation, we're going to talk about how code signing can help you have the best experience with Windows. We'll start with a brief introduction to code signing, talking about why it's important and 2 types of signatures you want to sign your code potentially with. The signing requirements section for key Windows technologies and kernel verification will answer 2 essential questions. The first is, what kind of files do I want to sign? And what special requirements do I have for signing these files for these scenarios? After that, we'll cover the best practices for test signing and release signing. This includes procedural information, including command line syntax, and it has best practice guidelines for securing your release process to make sure you only intend what you only sign the code you intend to sign. The last section reviews sample code, which demonstrates how applications can verify that their updates are coming from the trusted source prior to installation. So, why is code signing important? Well, for starters, it securely identifies the publisher. It also ensures that the binary, which is downloaded from a potentially unsecure source, arrives in the intended state that the publisher produced the file in. It ensures that the file cannot be undetectably tampered. With these 2 pieces of information, users can make a more informed trust decision as to whether or not to run or install the binary. Many Windows features take information from the signature and display it to the user to help them make the trust decision. In certain settings, features actually require signatures to be present on the binary before running the application. This we'll discuss later in the next sections when we go over key scenarios and technologies. Finally, code signing provides some level of brand protection to application providers. If your code is signed, it is harder for a malicious entity to tamper with your code or pass code off in your name because they won't have access to your code signing certificate. There are 2 types of ways to sign code. The first is embedded signing. This is the more intuitive form of signing, as the signature resides in the file that's signed. You don't have any management problems trying to manage multiple files, and the operating system can very easily detect the signature within the file and find it right away and verify your file quickly. Unfortunately, embedded signatures are only supported for executable files and certain installation formats like MSI or archive files like CABs. For files that don't support embedded signatures, you can use a catalog file in order to sign your content. In this case, your file is hashed, and that cryptographic hash is placed in a catalog file, which itself is then signed. This is slightly more tricky to manage because you have 2 files you have to keep in sync. Whenever you update your application, you need to update your catalog file as well. You also need to register the catalog with the Windows catalog database. That way, Windows knows where to find the hash and signature for your particular file. This can be accomplished with crypt cat admin add catalog. This does require administrative privileges in order to perform. So it's another reason to use embedded signatures when you can. So the features that we're covering today all will verify files with embedded signatures. Some of them will also support catalogs. We'll go through the specific requirements for each key technology in the upcoming sections. So now let's start with Internet Explorer. Internet Explorer only recognizes embedded signatures. ActiveX Control installers must have embedded signatures, otherwise they will not be installed. In Windows 7, the Internet Explorer introduced per-user ActiveX controllers. These have the same signing requirements as per-machine ActiveX controllers. Internet Explorer also verifies the signature on files that are downloaded from the internet, rather executable files and MSI installers. In this case, they take the authenticated application and publisher information from the signature and display it to the user before they either run or install the file. If the file requires administrator privileges in order to execute, often it will display a user account control prompt. In Windows 7, this is what the user account control prompt looks like. You'll notice that the program name Virtual Earth 3D was gotten from the signature. Also, the verified publisher, Microsoft Corporation, was acquired from the certificate whose private key was used to sign the file. Other types of applications trigger this UAC prompt. The key applications you should worry about as an application developer are those that require changes to require administrator access to make change to system settings or system files. Specifically, the Windows directory is very often configured by administrator applications, or registry settings under HKey local machine. Now, ideally, with UAC, the best thing to do is to actually write to user directories or HKey current user, and therefore you won't even need administrator credentials. But if your application requires administrator credentials, you need to add an application manifest, either embedded within the file or beside the file in the local directory, and set the requested execution level tag with the level attribute equal to require administrator or highest available access. In this case, UAC will verify the signature on your file and display your publisher and application information correctly. Applications that drive input to the user interface also require signatures and applications. These application manifests. These applications include on-screen keyboards or accessibility applications designed to make Windows easier to use for certain users. In this case, the application manifest requires the requested execution level tag with UI access equal to true. Other ways that UAC dialog can be displayed is if the application is launched using right-click Run as Administrator. If your application instantiates a COM object with administrator credentials, meaning using co-create instance as admin, UAC dialog will also be displayed. Finally, if you're installing a system-wide MSI, the UAC dialog is displayed because the install package has to write registry settings to HKey local machine. Any updates to system-wide MSI packages should also be signed. In order to sign a file for UAC, the first thing you need to do is set the application description in the signature. We'll have specific command line examples later in the presentation to describe how to do this. Next, if you're updating your system-wide MSI file, make sure to use the signing certificate listed in the MSI patch certificate table. In this case, MSI will be able to install the update without launching a UAC prompt because that update will be trusted by that system-wide MSI installation package. Now note that signing certificates do expire over time, so you need to make sure you update your MSI patch certificate table before your signing certificates expire with new, fresh signing certificates. Otherwise, your next update package will require a UAC prompt. Now again, embedded signatures are recommended for UAC, but not required. If you do use catalogs, you do have to use administrator privileges in order to register catalogs, and this also requires, again, you guessed it, a UAC prompt. So embedded signatures are preferred. The next key technology is software restriction policies. Now, many people may not necessarily be familiar with this technology. It's used by IT administrators in order to restrict the set of applications that can be run in their managed environments. The motivation here might be to make it more difficult to install malicious applications, be in compliance with regulatory rules, or just restrict the applications that are running in the environment to those that have been application compatibility tested for use with the other applications in the environment. This feature uses allow rules based on file hash, file path, certificate hash, and publisher name. In Windows 7, Software Restriction Policies version 2 introduces publisher rules. These allow IT administrators to make very powerful policies based on the product name and the product version. For example, as an administrator, you could specify Office Communicator version 2.0 and above will run in your environment. This means that Office Communicator can be updated without invalidating any of the policy rules, which makes it much easier for IT administrators to manage. In Windows 7, enterprise customers that get access to early builds are very excited about this feature and are planning to deploy it with publisher rules. If you want to make sure that your application works well in these environments, the best thing to do is follow the following requirements. 1, set the product name and product version in your install package, your executable binary, and all runtime DLLs. Make sure they match. Binaries that are localized and may have multiple product names and versions with different languages, make sure it is the first product name listed in the string table that matches your MSI installation file. Also, even if you're not using an MSI file, make sure to use MSI naming and versioning conventions, meaning whenever you update, increment your version number and use a 64-character max for your product name. You want to make sure that you sign all the files in your package, the primary executable, all DLLs, and if you have an uninstaller, you want to sign that too, so the user can remove your application from your environment if they decide that they don't want to use it necessarily. Finally, if you repackage third-party DLLs, you really shouldn't re-sign them. Make sure that the third-party publisher's signature remains on that package. Otherwise, they may come back to you with questions as, why are you pretending that you authored this binary? And when possible, try to use the same signing certificate. Now, signing certificates do expire, but when you register for a new signing certificate, make sure that you use the same organization, locale, state, and country fields in the signing certificate. This is required in order to maintain consistency between multiple versions of the certificates in the SRP publisher rule policy. Also, as with UAC, embedded signatures are recommended. Although in this case, the reason is catalogs provide a less performant experience. And the check is done when the file is loaded, and that's a time the user is particularly sensitive to delays. So embedded signatures here are greatly preferred. So the previous set of key technologies worked better if you had a signature. In kernel verification, a signature is mandatory in order to get the file to load into memory for the application to even work. The first class of policies that are enforced here are for x64 kernel modules. You need a special signing certificate in order to sign these called a kernel code signing certificate. These can be acquired from certification authorities listed on the WHDC site, or you can get a Windows Hardware Quality Labs signature on your file. Now, if you're not using WCL, you need to also include a cross certificate with your signature. These certificates are also available on the Windows Hardware and Device Center website. Now, it's worth noting that the Windows Signature UI, right-click on the properties, File Properties, Digital Signature tab, the actual cross certificate won't necessarily be displayed. In order to see the cross certificate, you need to use signtool.exe from the Windows SDK, and you need to use the verbose output to verify that the cross certificate is in fact in the certificate chain and is present in the signature. Note that kernel modules can be either catalog or embedded signed. If you're using a catalog and you're using plug and play, this catalog will be registered on your behalf by the plug and play installer. If you're not using plug and play, you need to use cryptcat admin add catalog in order to make sure that your catalog is registered properly. For kernel modules loaded 10 minutes after boot, it is highly recommended that you have an embedded signature for best performance. This is because Windows has to take extra time to enumerate through the system catalogs to find the specific file hash and catalog that is used to verify your particular file. Note that you can have embedded signatures in addition to catalog signatures. However, INF2CAT and signability.exe, tools used in the Windows driver kit for creating catalogs, do not embedded sign the file. You need to sign it separately using signtool.exe. The second class of kernel drivers that are checked using kernel verification policy are those that call kernel patch protection APIs. Kernel patch protection is also known as PatchGuard. It protects structures within the kernel to ensure they cannot be hooked or tampered with by malicious applications. However, there are security applications and manageability applications which need the functionality that were previously exposed through these kernel structures. This functionality is now exposed through the kernel patch protection API. In order to access these APIs, your component needs a signature. Your component needs to also be marked with link.exe/force integrity. This mark ensures that that your component is verified whenever it is loaded into memory. Also, this policy is required on both x86 and x64 architectures. The signing procedure and requirements are the same for x64 kernel drivers. So you need to either have your component signed by WCL or use a kernel signing certificate to sign the component, including a cross certificate. So now that we've gone through the key technologies and kernel scenarios that require signatures for a best experience, we can go through some of the procedures for test signing applications and release signing them, as well as go over some high-level guidelines to make sure that your signing process mitigates risks of signing files you don't intend to sign or compromising your private keys. So first, why test sign your code? Well, you don't want to sign pre-development code with your release signing key, but you still want to test it in verification scenarios. The easiest solution is to issue test keys, which are trusted only in your test environment. You can give developers ready access to any keys, and if the key is compromised, it doesn't matter, you just create a new one. It's also less overhead for developers to use because they can generate test certificates using tools they can acquire from the Windows SDK. You don't have to download the entire SDK. You can save yourself a little bit of time by using a web install and only installing from Developers Tools, Windows Development Tools, Win32 Development Tools. The first step in test signing for IE, user account control, and software restriction policies is to generate a self-signed certificate. You can use this make cert in order to generate such a certificate with the command line listed below. This will import the certificate into your personal certificate store, and will generate a test.surf file, or whatever you want to name it, which you can then use to configure machines in your test environment. You need to import this test certificate into the trusted root stores of the machines in your environment in order for them to trust your test-signed application. You can use either the Windows UI by double-clicking on the certificate to import it, or you can use Cert Manager using the command line syntax specified on the slide. The procedure to test, sign, and verify the binary uses signtool. Important to note, /D is where the application description displayed by the UAC prompt is set. Also, /DU specifies a URL that may be displayed in certain certificate verification UI, signature verification UI. In this case, you're going to use signtool verify in order to verify that the signature was applied correctly. The /PA switch in the command line syntax below, or on the slide, specifies that applications signed with certificates issued from certificates configured in the trusted root store will be trusted. Testing for kernel verification is a little different. You have two options. The first option is best during early development. You can disable the verification policy by attaching an active boot or kernel mode debugger to the machine. Or you can select F8 during the boot sequence in order to disable driver signature enforcement. This allows you to load unsigned drivers into the kernel, and you don't have to test sign for your intermediate pre-release builds. However, the F8 boot option only lasts for one reboot cycle. So later, you may want to enable BCD edit test signing on, which turns the test signing feature on for kernel verification. In this case, you want to generate a test certificate just like you did in the last example with MakeCert, and you want to sign the binary just as you did with SignTool. However, you do not have to import the certificate into your signing machine, because in this mode, the kernel verification policy will trust any signature, not just the ones that are trusted in the machine certificate stores. Release signing is very similar to test signing, only this time you have to acquire a real signing certificate. Some examples of trusted CAs include VeriSign, Thought, GlobalSign, or Komodo. You have to import the publisher signing certificate into your personal certificate stores on the signing machine. This can be done during the enrollment process, or some CAs will provide an SPC and PVK file or PFX file. You can convert SPC and PVK files to a PFX file, and then import the PFX file into the system certificate stores using certutil.exe, which ships on newer versions of Windows. The command line syntax to embedded sign and verify the signature is very similar. However, it's worth noting that the /t switch lets you specify a timestamp server to timestamp your signature. This is very important. Without a timestamp, a signature will expire when the signing certificate expires, and then your application will no longer be verified. Once you timestamp your file, provided it's during the validity period of your signing certificate, then the signature will remain valid indefinitely. The syntax for verifying the file is the same. Also, some people have been code signing for a very long time, and they might be using a legacy tool called SignCode. This tool defaults to using MD5, which is not a cryptographically secure hash function. So it's important that if you're doing that, you should upgrade to using SHA-1 or upgrade to using SignTool. Release signing for kernel verification is very similar. Only this time you need to acquire a kernel certificate from either VeriSign or GlobalSign or other CAs mentioned on the Windows Hardware and Devices Center website. You also have to acquire the matching certificate from the same location, cross certificate from the same location. Now, the command line syntax again is similar, only this time during SignTool signing step, use the /AC flag to specify the cross certificate. In the verify step, use the /KP switch to specify kernel policy. You also specify the /verbose option to dump the certificates which were put into the signature. You want to check to make sure that the cross certificate is displayed, to make sure that it is properly present. So now we've talked about the procedural information. Now we're going to go over some guidelines for how you can sign your released binaries securely. This is important because access to your signing process and the private keys in those signing processes are essentially giving access to someone to represent your company with a certified version of your company's identity. Compromised keys can be used to sign malware with your company's identity, and that can misrepresent you. Best practices in the following sections will help you mitigate this risk. Now, it's worth noting that you should only apply these best practices in accordance with the value of the key and the risks that you believe that you face. And you have to balance the security measures you take with cost, usability, and the efficiency impact that implementing these measures take. So basically, find what works for you and stick to it. The first most important principle is to protect the private signing keys. One way you can do this is to store the keys in hardware, either using a hardware security module or a smart card. Secondly, you want to protect the signing environment. If someone can take your HSM or smart card and leave the building, your private keys can still be compromised. Below are some ways that you might implement physical security to ensure that you can maintain the integrity of your signing process. Also, you need to ensure that the binaries submitted to your signing process are the binaries that are intended to be submitted and intended to go out to the public. It's recommended you require approval from multiple trusted sources before signing your binaries for release. Also, if something goes wrong, you want to make sure you've audited the submissions to your code signing process to ensure that you can track down what happened and hold the responsible parties accountable. We already talked about test signing, but it's worth repeating. Make sure that you only sign your binaries that are intended for the public with your release keys, and use test signing for your non-public releases. Virus scanning is fairly self-explanatory. It helps prevent you from accidentally signing malware and then releasing it to the public. If you want to make it more difficult to compromise your code signing process, you might separate your auditing and virus scanning from your signing operations. This just makes it harder for an attacker to compromise your entire process. If your private key is compromised, you need to contact the certification authority that issued the code signing certificate and have that certificate revoked. If you properly timestamped your binaries, this will ensure that the revocation notification will not invalidate any of your previous signatures, but it will keep an attacker from creating new signatures with your compromised private key. Also, some people like to integrate their signing procedure with their build process. Now, if you're automatically signing the output of your build process, you should be aware you're expanding your security boundary from your signing operation to your build operation. And as such, you should implement a layered security approach and make sure that you're authenticating and auditing the submissions to your build process so you can have the same protections as for the signing process. If you are signing over a network, it's highly recommended that you authenticate the endpoints and ensure message integrity between those endpoints to ensure only authorized computers can be sending submissions to your code signing service. If possible, you should isolate your build, signing, and general use networks to make sure there is less chance that others can get access to the signing network who aren't intended to get access. You can also employ intrusion detection and network monitoring to ensure that you can detect any sort of attacks if they occur. So now we've talked about how to sign your code, how to secure your signing process. Now we're going to talk a little bit about verification. There's a new set, well, not really new, but there's a set of attacks which are possible when applications automatically download updates from their update servers and install them without verifying the content. It's very possible for a malicious attacker to redirect those requests to a malicious server and then download content that could have bad consequences onto a user's machine in the name of your application. This can be mitigated by verifying the contents of the update package prior to installing it. Once a binary is signed, your client becomes resilient against network redirection attacks and compromised distribution servers. Windows has been signing their updates for a very, very long time now. There's really two good ways to verify the integrity of update packages. The first is to verify the publisher's signing key. We have some sample code to describe how this is done. In this case, you're going to take a SHA-1 hash of the public key and put that on a list of trusted hashes. Now note, when a new certificate is issued after the previous certificate's expired, you can either reuse the same signing key, or you need to update your trust list with a SHA-1 hash of the new signing key. Second option is to verify the publisher's name. In this case, you want to verify the SHA-1 hash of the root certificate's public key. Note, root certificates usually don't expire for a very long time. And you want to ensure that that certification authority, the one that issued you your certificate, is the one that was used in order to sign the package. You then verify the subject name fields in the signing certificate to ensure that it matches your company. And you're depending on your certification authority's policies to never issue anybody else a certificate with your company's name. Now we're going to go through some sample code in order to demonstrate how this is done. So let's switch over to Visual Studio. This example demonstrates how you verify the trust in the publisher's signing key. The first step is to get your signing certificate and dump the SHA-1 hash of the key using certutil/v. The key in this verbose output, you'll get the SHA-1 key hash. This SHA-1 key hash will be hard-coded into your signing application, or verifying application. The first function we're going to demonstrate is key trusted? This function takes a certificate, it takes a list of SHA-1 key hashes, and it compares the key information from the certificate, hashes it with SHA-1, and then compares it to the list of keys that was passed to it. If the key is trusted, it returns true. If the key is not trusted, well, returns false. The next function is publisher key, is trusted publisher key. This takes a certificate chain context. From that, it extracts the simplest chain, and from that, it extracts the publisher's signing certificate, which will be the leaf certificate, first one in the list. It will then take that certificate and give it with the trusted key list to the function we just discussed, previous function we just discussed. Now we have the kind of overall function which verifies the signature. Is file publisher trusted? This function relies on WinVerify_Trust and the WinVerify_Trust generic verify2 policy. The function starts by initializing a WinTrust data structure. You'll notice that revocation is enabled, meaning if your key is compromised, you can revoke the key. There's no UI, and it verifies the entire chain except for the root. Additionally, we are verifying an embedded signature. You can see the WinTrust file info, which is being initialized right there. The signature is verified by calling WinVerify_Trust. The provider data is then retrieved from that function call using WT helper prov data from state data. From the provider data, we get the signer information with WT helper get prov signer from chain. From that, from the signer provider information, we were able to get the certificate chain. And from the certificate chain, we can use the functions that we described above, is trusted publisher key, in order to verify that the publisher certificate's key matches the SHA-1 hash that is hard-coded into your application. And if we got this far, we can trust the file. Afterwards, we clean up some state and return the results of the function. So that's how you trust a publisher's certificate key. Now we have an example about name trust. The first step is to understand the SHA-1 hash of your root certificate's signing key. This can be done, again, using certutil/v, and you're looking for the key ID hash, SHA-1 hash. Once again, this is hard-coded within your application. Next, you're selecting which fields you want to verify in your publisher's subject name. In this case, we're going to use organization name, locality, state or province, and country name. These fields should stay consistent between certificate versions. You can also use certutil-v in order to dump this information from your signing cert. Then you hard code these fields into your application. In this case, we're using Contoso, Redmond, Washington, US. Once again, we have the isTrustedKey function, which verifies that the SHA-1 hash of a given certificate is on the list of trusted SHA-1 hashes. This will be used by isTrustedRootKey in order to ensure that your root is trusted. This takes a certificate chain very much like isTrustedPublisherKey, only in this example, we are getting the root certificate from the end of the chain, not the beginning of the chain. Now we have isTrustedPublisherName. This takes a certificate chain context and extracts the publisher certificate from the chain context. Then it loops through the fields in the subject name to ensure that all the required fields are present and gets the length. Note that a matching certificate must have all attributes. It does a second pass to ensure that the fields match, and if they match, the publisher certificate is trusted and this function returns true. Now, the isFilePublisherTrusted is the overall function which verifies the signature. Once again, this uses WinVerifyTrust, and it has the same initialization using revocation and specifying a file info structure for an embedded signature. Once again, it uses WinVerifyTrust to verify the signature. It extracts the provider data, and then it extracts the signer data. And from that, we can extract the certificate chain context and provide that to isTrustedRootKey to verify the certification authority's root key, and isTrustedPublisherName to verify the name on the publisher's certificate. And if we make it through both of these functions, the file is true. And once again, there's some cleanup. So that is how you can verify the contents of your update packages. To conclude the talk, I want to leave you with a few call to action items. One, sign your applications so you can have the best experience with Windows. You want to make sure that you meet the scenario-specific requirements for Internet Explorer, user account control, software restriction policies, and kernel verification scenarios. You want to make sure that you verify, you protect your release signing process, and make sure that you sign and verify all of your application updates. You can send questions to Microsoft Public Security Crypto, the news group, There's also a plethora of materials online that talk about code signing best practices, kernel mode code signing, and other details. Additionally, the sample code we just reviewed will also be downloadable from the web with this talk. So with that, I want to conclude the talk by saying thank you for listening. I really appreciate your time. It's been a pleasure.